We will continue with this magneto-optic effect with the Faraday rotation. Now, this transmission mode, look at the microscopic description picture, Zeeman splitting, then other configurations like longitudinal configuration, circular magnetic birefringence, Faraday effect will continue with that. Then the transverse configuration, linear magnetic birefringence, Voight effect, reflection mode, this MOKE polar, longitudinal and equatorial mode, absorption mode, measurement of rotation angles. So, as I mentioned that the parallel configuration is known as the Faraday effect, which we will again continue for the perpendicular configuration. Voight effect will take up next. So, this magneto-optic effect phenomenologically this is related to the normal Zeeman effect. Magnetic field causes the splitting of the energy levels, which shifts the original resonant frequency nu of an absorption line to slightly higher and lower frequencies nu 1 and nu 2. Therefore, a double dispersion effect is generated. LCP light is dispersed at a frequency nu 1, whereas the right circularly polarized light will be dispersed at a frequency nu 2. So, effectively the two frequencies of the light will be different. Therefore, there will be a birefringence. See that when it is unperturbed, then you have this wave function and when it is perturbed, then this wave function in presence of this there has been a shift, there has been a small dipole which will be the superposition of this S like and P like orbitals. So, this is expansion of the unperturbed orbitals. Now, this P orbitals P x and P y, they will correspond to this P x, which is P plus, which is equal to P x plus I P y, and P minus. These are the two different sense of rotation. You can see that P x, this is minus of I P y, this is plus of I P y. So, these two, and they will correspond to the transition which are this right circularly and left circularly polarized light will be the interaction. So, now this spin orbit coupling will split this L equal to 1 into effectively 4 lines, 4 energy levels which are given by this. This is already known, and there will be transitions from this to this, which corresponds to this right circularly, from here to here, this corresponds to this right circularly, whereas this transition will correspond to this left circularly, and similarly this transition will also correspond to the left circularly. So, without magnetization, these are the energy level, and then with exchange splitting you have each of them split into 2 energy levels with upward and downward transition, and then this is the exchange plus spin orbit coupling. It results into these 4 transitions. Now, this causes the LCP and RCP component see different refractive indices, thus a retardation of one component relative to the other, that gives rise to a net phase difference between the two lights. And when these lights are emerging, these components combine to give an elliptical polarization, whose major axis is now rotated relative to the original polarization direction. So, the angle is called the Faraday rotation angle. You can see this, you have an input polarized light and the magnetic field is applied along the length of the medium, and you can see that the plane of polarization slightly rotates, and when emerging from the crystal, this has undergone a neat rotation of this much, that is represented by Faraday theta f, which is due to the Faraday, and this depends on the interaction length of the magnetic field with the optical light, that is L, and the magnetic field. So, this we have seen. Now, Faraday rotation is directly proportional to the magnetization m, and it is also directly proportional to the length of the light path within the material. So, this we have represented in terms of the external magnetic field B, and now it is in terms of the magnetization of the material. This proportionality constant, as I have mentioned, is called the Voight constant. It can be represented by the related parameters. Because of the linear dependence of theta on the internal magnetization, or in most cases on the external magnetic field, Faraday effect is called an odd effect, because it linearly the rotation is linearly proportional to the magnetization m or the magnetic field B. So, it is linearly proportional. The Faraday effect is referred to as the circular magnetic birefringence or magnetic dichroism, CMB. Faraday rotation, this we have seen that this Voight constant, it depends on the medium properties, ambient temperature, and also the wavelength of the light that is used to interact with the magnetic field within the medium. Now, we will continue this magnetization, the transmission mode. Magnetization in the sample could be due to the presence of external magnetic field, or it could be because of the internal magnetization, as I have mentioned. This magnetization could be parallel and perpendicular. Now, we will consider the perpendicular configuration, which is the Voight effect, and when the magnetic field is perpendicular to the optical path, the incident optical beam is linearly polarized, then a different type of interaction with the material occurs. This effect of perpendicular configuration is known as this is the definition of this Voight effect. Instead of now, this mechanism for this we will look at in a slightly different way, that instead of looking at the decomposition of a linear or a plane polarized light into the left circularly polarized light and right circularly polarized components, we will see that the electric field of the light is now either parallel or perpendicular to the magnetic field. The parallel component is no way affected by the magnetic field, as you know that this electric field which is parallel to the magnetic field will not affect this, whereas the cross magnetic and electric field, that is the two perpendicular components, they will oppositely interact with. So, this effect was discovered later in 1899. The unequal absorption or phase shift of the linear polarizations which are parallel and perpendicular to the magnetization direction. So, the light beam the polarization of the light beam is parallel and this is perpendicular. It may be somewhere in between this. So, we will decompose this polarization of the linear polarized light into parallel and perpendicular components. There is the relevant permittivity of the medium in presence of the magnetic field. We will not talk about this. This is the direction of the magnetization, and this effect is quadratic in the magnetization, that is m square, and this is also called the Cotton-Newton effect or linear magnetic dichroism. So, in that case this intensity, the difference of the intensity due to the perpendicular polarization and parallel polarization will be the effective intensity available when the light beam is exiting from the medium of interaction. So, this interaction results again in a difference of the refractive indices, that is plus minus delta n. Thus, a birefringence of the two perpendicular components will be observed. This will lead to a rotation of the plane of polarization, that is theta v, which will be equal to your k 0 twice pi upon lambda delta n, and is proportional to the length of the medium in which the optical beam interacts with the magnetic field. This effect results in a linear magnetic birefringence, and is independent of the orientation of the field. It is axial. It is proportional to the square of the magnetic field, m square. If it is we call the, if we look at the magnetization of the material, and if we consider the field, external magnetic field, then it is proportional to a square, and that is why this effect is called the even effect. So, in the reflection mode, now we have reflected light from the surface of the magnetized material in all different configurations of the direction of magnetization with respect to the optical part. This effect is known as the Kerr effect, magneto-optic Kerr effect. You see, in Kerr effect measured in the reflected light, and it was discovered in the year 1876. An incident beam is incident and is reflected in presence of the magnetic field, which is intersecting with this material, and the result will be the change in the polarization properties. Whereas, in the Faraday effect, which we have seen that an optical beam is passing through the medium, and the medium properties will be affected. The optical properties of the medium will be influenced by the external magnetic field. So, this magneto-optic Kerr effect are called MOKE. This you have an incident, let us suppose you have an incident S polarized light. We have learned what is S polarized light and P polarized light in the beginning of this lectures. S polarized light, this is the input polarization, and the perpendicular component is the P polarized light. So, when they are incident on the surface of a material of a medium which is in a magnetic field, then the reflected light will also contain P polarized light, because there was no P polarized light initially, it was purely S polarized light, and now that on reflection we can see a small component of the P polarization has appeared because of the reflection, and there has been an effective rotation of the plane of polarization. You can see that there has been an effective rotation of the plane polarized light. On reflection at magnetized sample, P polarized wave also appears as a result of this. Three different configurations of the light with respect to the magnetization in the sample. This tells you that when the light is incident, there could be three possible configurations with respect to the magnetic field. Magnetic field could be along this, could be along this, or could be along this. So, you have three possible orientation of the magnetic field. These are the orientations. Let us suppose we call this is x, y and z axis. So, along z axis, if the magnetic field exists, then and the incident light is being incident on this surface at this point and getting reflected. So, this configuration is the polar configuration, whereas if the magnetic field is along this direction, that is along y direction, and the light beam is incident and reflected, this configuration is called the longitudinal configuration. It is along the plane of the incidence of the light beam. The other configuration is the transverse MOKE configuration, that is in which the magnetic field is now perpendicular to the plane of incidence, and you have the optical beam which is incident here and reflected this. So, these three effects are in general different. So, these are the corresponding permittivity relations which are used to analyze the properties of the reflected light in presence of the magnetization of the material in three different orientations. So, analysis of the reflection mode is actually quite involved because of the oblique nature of incidence, and one expects a mixture of all possible polarizations in each direction. A simplified analysis which is based on the electromagnetic boundary conditions at the reflecting surface for polar configurations at normal incidence gives some insight into the effect. For example, if you consider the Fresnel coefficient for this case, for the case of polar incidence, you see this one, this polar incidence, you have incident light and you have reflected light. It can have S polarized light and P polarized light, both the components could be present. In that case, because of reflection, the Fresnel coefficients for normal incidence, the reflected amplitude will contain this refractive index term, and this gives the hints dependence of R on n, the reflectivity. This reflection coefficient, it depends on n, that gives you the hints that the difference in the value of n for the LCP and RCP, because LCP and RCP they will be again composed of the polarizations, and as a result there will be a difference in the amplitude and phase shift between the two lights. If the incident light is now linearly polarized, the reflected light will be elliptically polarized because of the difference in the amplitude and also the phase, since the two circular components that compose the incident beam will no longer be of equal amplitude because of the reflection. So, because of the reflection coefficient, the two components will have different amplitudes on reflection from the surface, and as a result their amplitudes are different, and also they are in phase, not equal in phase, and this will lead to, that is as it has happened in the case of Faraday effect. So, there will be a change in the polarization. The main axis of the ellipse now rotates by an angle theta k, this k is for Kerr rotation. So, which is relative to the original direction of polarization. Angle theta k is very small, of the order of minutes. In the equatorial configuration, the components of the reflected lights as calculated show that the only component parallel to the field is affected by magnetization, and the reflected light will the amplitude of the reflected light is linearly proportional to the strength of magnetization, that is the parallel component of the reflected light, the amplitude would be proportional to the magnetization value. So, this is unlike this quadratic Voight effect, and which has the configuration is similar, but the effect is different. Because of the uniaxiality in the reflection mode for this equatorial configuration, when magnetization direction is reversed, that is antiparallel, then affect this directly the intensity of the reflected light, and this change can be detected without using an analyzer, which means that considerable increase in the efficiency. So, intensity measurement will be visible, and that tells that the rotation is quite large. A typical value of theta k in the visible range is about 10 minutes. Now, this measurement of rotation angles theta f, theta v and theta k. So, rotation they can be measured by different methods. Static method involves using babinet compensator, polarizer and analyzer setup as a function of the change in the magnetic field. It could be by a dynamic method in which the magnetization is periodically switched on and off, and one can use a lock-in amplifier that records the intensity variation as a function of the change in the magnetic field. So, this absorption mode in this case, this effect is the difference in the absorption coefficient of the polarizations, that is polarized light, that is LCP and RCP components of the light. This the difference of the polarization, they are absorbed by different amount by sample of magnetized which is in the beam direction. Then linear magnetic dichroism that also exists, which is similar to the Voight effect, and magnetic field is transverse to the light path in this in this particular configuration. CMD and LMD, that is this circular magnetic dichroism, linear magnetic dichroism, they can give some insight on the, they are used to can be used as in experiments to have an insight of the band structures of crystals and the magnetically induced transition levels. To study this property, they are used this circular magnetic dichroism and linear magnetic dichroism properties, magnetic field used probing. Now, this we will just look at the few methods of magneto-optic measurements using cross polarizer, vibrating polarizer, measurement of ellipticity. So, this Cross-Nicol prism technique, here you have the source of light, then you have a pair of nickel prisms, one is the polarizer, the other one is the analyzer, and you have a magnetic field which is perpendicular to the direction of the beam path, and you measure the intensity of the light because of this Cross-Nicol prism. For this kind of amplitude modulation setup, we have a pair of polarizers, one is called polarizer, the other one is analyzer, and if there is a rotation of the polarization axis of the optical beam, then the intensity varies, which is detected by a detector placed in the path of the exiting light, and the intensity variation as a function of the rotation of the plane of polarization of the optical beam is shown here. So, this is how, this is the rotation angle and this is the intensity. So, it goes through a maxima and then it becomes a minima, and this will be periodically as you keep on increasing the magnetic field. So, this is again the depends on the length of interaction of the magnetic field with the optical beam. Vibrating polarizer technique, here also you have a pair of polarizer and analyzer, but this time this magnetic field is along the direction of the light propagation. You can see this, you have a crystal, magneto-optic crystal, and the light is travelling through it, and you measure the detected intensity as a function of the magnetic field by a detector at the light output. The rotating analyzer technique, in this case you have the polarizer which is fixed and the analyzer is as a function of magnetic field, because this is again the parallel configuration, Faraday configuration, in which the magnetic field is along the direction of the light propagation, and as a function of the strength of the magnetic field, the rotation occurs, and because of the rotation there will be a fall in the light intensity, but if you rotate the analyzer, then you can measure the same intensity at different rotation angle of the analyzer. So, and you note down the angle of rotation of the analyzer. So, from there we can make an estimate of the magnetic field, the rotation as a function of the magnetic field. Then this Faraday rotation, this is also a very good and interesting laboratory experiment. You have a polarizer and a source of light is passing through the polarizer. So, therefore, the exiting light is a plane polarized light. You have a magneto-optic material, and or else it could be a current passing through a solenoid, which is given by I equal to I 0 plus delta I sin p t, and as a result, if the because of the variation of the current, the plane of polarization, the variation of the current, the magnetic field also varies, and which will result in the change in the periodic change in the plane of polarization, which is detected by a detector, this magnetic field, and this detector current they are fed into an op amp, which is again connected to this system. So, in this way, which is called a Faraday modulator, in which as a function of the input current, the magnetic field changes, magnetic field in turn changes, varies the plane of polarization, and because you have an analyzer. So, this is placed between a polarizer and an analyzer, therefore, the intensity also changes. This change in the intensity will change the detector current, which will be added through an op amp, and then in the differential mode, and you get this Faraday rotation measurement. Now, this ellipticity measurement, in this setup, you have the electric field E 0, which of this elliptically polarized light, which can be decomposed into E 0 sin eta and E 0 cosine eta, this one, and you have another component. So, this goes through a quarter wave plate, the resulting light can again be decomposed. So, this is the direction of the electric field E prime, which can be written as this, because it passes through a quarter wave plate. We add a phase e to the power of minus I pi by 2, and effectively this becomes cosine eta I plus sin eta I. So, this is the direction of the rotation of this plane polarized light. So, in this way we can measure the ellipticity of the elliptically polarized light, which is the due to the as a function of the magnetic field. So, we discussed this transmission mode, the microscopic description from the Zeeman splitting, longitudinal and circular magnetic birefringence, Faraday rotation, Voight effect in the 3 different configurations of the reflection mode, polar, longitudinal and equatorial mode, absorption mode, measurement of the rotation angles because of the magnetic field. Thank you very much.